Welcome to the deep dive. Today, we're really digging into some cutting-edge research on sequence models.
That's right.
We've got this paper, you, our listener, pointed us to millions of states designing a scalable MoE architecture with RWKV-7 meta-learner, and you also sent over some great notes putting it all in context.
Yeah, Xiao, Zhiyuan, and Yueyu's really interesting work.
Definitely. So our mission today is to unpack the core ideas behind this metastate architecture, specifically how it tackles the scalability problems we see even with models like RWKV, let alone transformers.
Exactly. It's trying to solve some pretty fundamental challenges. I mean, we all know transformers have been dominant since what, 2017, Maswani et al. Attention is all you need.
Right, the game changer.
And their strength is that self-attention, the multi-head attention, right? It lets the model look across the whole sequence, grab long-range dependencies, super powerful for understanding context.
Absolutely. That context window is key. But, and it's a big but we've hit before, scalability is the Achilles heel, isn't it?
Precisely, that quadratic complexity. As your sequence gets longer, the computation just explodes. N squared.
Yeah, n squared. So double the length, 4 times the compute roughly. That gets out of hand fast for like processing a whole book or something.
Totally prohibitive for really long contexts. And that's where state-based models like RWKV come into the picture.
Right, the alternative approach, Peng and colleagues looking towards RWKV7.
Exactly. These models aim for linear complexity. They keep an internal state, update it step by step. No need to look back over everything all the time.
So much more efficient for long sequences. Linear sounds way better than quadratic.
It is for that specific aspect. But as the paper we're looking at highlights, even RWKV7 has limitations this new metastate approach wants to fix.
Okay, so what are the problems Metastate is targeting with RWKV7 specifically?
Well, there are two main things, really. First, this idea of token parameter interaction. It's a bit subtle.
Okay,
In RWKV7, the input tokens affect the state, obviously, but there isn't a strong built-in way for those tokens to directly change how the model's parameters work on the fly during processing.
so less dynamic adaptation based on the specific input.
Sort of, yeah. It potentially limits its flexibility. The second big one is scaling up the model itself.
Right.
If you want a bigger, more capable RWKV model, you basically have to retrain it all from the beginning. That's expensive, time-consuming.
Yeah, no easy way to just like add more capacity incrementally.
Exactly, not easily. So that's the setup. RWKV is efficient linearly, but maybe lacks some dynamic interaction and easy scalability.
Okay, that makes the motivation really clear. We need that efficiency, but also adaptability and smoother scaling. So let's get into Metastate. What's the core change they're proposing?
Fundamentally, Metastate is built on top of RWKV7. It's an extension. The absolute key innovation is they take out the standard feed-forward network, the FFN.
Which is a pretty standard block in these things.
Very standard. They replace that SFN with a completely new, fully state-driven layer. They call it the metastate layer. That's the heart of it.
Replacing the FFN with a metastate layer. Okay. And how does this new layer help with that token parameter interaction problem we mentioned?
Right, so this is where they drew some inspiration from another recent paper, Token Former from Wang and others in 2024.
Token former. Okay.
Token Former had this neat idea. Treat the model's parameters themselves like another sequence of tokens. Then you could use cross-attention between the input tokens and these parameter tokens.
Interesting. So parameters become interactive.
Yeah, and it helped with scaling too. Now, Metastate takes that concept interaction between tokens and parameters, but does it in a totally different RWKV-friendly way.
How so? Different how?
Well, token former uses cross-attention, right? Which means softmax calculations, which RWKV is designed to avoid because they're computationally heavy.
Oh, okay. So metastate needs a non-attention way to get that interaction.
Exactly. They achieve it within the state-based logic of RWKV. No softmax needed.
Clever. So same goal as token former, different path. How does this metastate layer actually do it then? You mentioned a specific component.
Yes, the self-state encoder, or SSE. This is probably the most ingenious part of the design.
Self-state encoder. Okay.
What they do is they cleverly repurpose part of the existing RWKV state, the weighted key-value state, or WKV state.
The model's own memory, essentially.
Precisely. They take a piece of that evolving WKV state and use it as the weights for a transformation.
Wait, they use the state itself as a weight matrix?
Effectively, yes. For each head in the model, a chunk of the WKV state acts as the matrix, let's call it WS. The input to the metastate layer, say XD, gets multiplied by this WS, and then they apply a ReLU activation, so ReLU XX.
Wow. Okay, so the model's current understanding of the sequence captured in the WKV state directly shapes how the next piece of input is processed in this layer. That's very meta,
It is, and the benefits are significant. First, you get that token parameter relationship encoded, but it's done via a linear transformation, which is fast.
right?
Second, and crucially for RWKV's whole philosophy, there are no new trainable parameter matrices introduced for this core interaction and no expensive softmax. It reuses existing state information.
Super efficient. They baked the interaction in without adding much computational baggage. Very elegant.
Exactly. It addresses that first limitation in token parameter interaction really nicely.
Okay, so that handles the interaction part. What about the second limitation, needing full retraining to scale up? How does metastate help there?
This involves something they call state autoregressive evolution in the metastate layer.
State autoregressive evolution? Sounds complex.
The idea is that the metastate at time t, let's call it MISC, isn't just calculated from the current input. It depends on the previous metastate, MS.
Okay, makes sense for a state model.
And also on bits and pieces from the WKV state, like a decay rate WT, a removal key hat, an in-context learning rate at plus the outputs from that self-state encoder we just talked about, CTT.
Right, the real USO output.
Exactly. There's an equation in the paper showing how these combine. MS equals MS plus DTT-ZT. The specifics are mathematical, but the key point is the state evolves based on its history and the SSE processed current input.
Okay, I see the stateful sequential update, but the link to scaling the model, how does this equation help with that?
The link is through that WKV state again. Remember how the SSE uses part of the WKV state? Well, the WKV state itself contains what you can think of as the model's learned parameter tokens, or its capacity.
Ah, okay.
So the idea is if you want to increase the model's capacity, you can simply expand the size of the WKV state, give it more dimensions.
You make the internal state bigger.
Right. And because the metastate layer's operations are defined relative to this WKV state, expanding the WKV state naturally expands the model's representational power without having to throw away the existing learned parameters and retrain everything.
So you grow the WKV state, and the metastate layer can leverage that extra capacity. How does that work with the existing parameters? Do they stay?
Mostly, yes. The core logic of the metastate layer, how the SSE works, the autoregressive update that stays the same. When you scale up by expanding WKV, you mainly need to adjust the layers that project into and out of the metastate layer.
The input and output projections?
Exactly. You might need bigger projection matrices, win and wout. You'd train these new parts, maybe fine-tune the existing metastate core parameters with a very low learning rate, or even keep them frozen.
Got it. So you're adding new capacity primarily at the interfaces while reusing the bulk of the learned knowledge. That sounds way more efficient than starting over.
Much, much more efficient. It allows for this kind of progressive parameter efficient scaling.
Okay, that tackles the second big limitation. Now, does it actually work? What did their experiments show?
The preliminary results look quite promising. They tested it on the Pile dataset's standard large text corpus.
Yep.
And they compared metastate models of different sizes, 150 million parameters up to 1.5 billion, against standard transformer baselines of similar sizes. They looked at cross-entropy loss, lower is better.
And how did metastate stack up?
Consistently better. Across all the sizes they tested, the metastate models achieved lower loss than the comparable transformer models.
Lower loss at the same parameter count? That's a good sign.
It suggests better parameter efficiency, yeah. But here's the really interesting part, the trend.
Okay.
The relative improvement of metastate over transformers got bigger as the models got larger.
Oh, really? So the gap widened.
Yeah. At 150 million parameters, the improvement was about 7.2%. At 1.5 billion parameters, it was up to 13.1% lower loss compared to the transformer.
Wow. That's strong evidence for better scalability, isn't it? If the advantage grows with size.
It certainly points that way. It suggests the architecture scales more gracefully, gets more bang for its buck as you add parameters.
That's potentially huge. Did they mention anything else contributing to the performance?
They briefly mentioned using a cross-encoder mechanism, maybe inspired by VAE's variational autoencoder.
Okay.
The idea, I think, is it might help manage the complex interactions between the input and the potentially very high-dimensional WKV state efficiently, but it wasn't the main focus.
So it sounds like a combination of the core metastate design, the SSE reusing state, and maybe some smart interaction handling, all adding up. what's the bigger picture here? What are the implications of where does this research go next?
Well, the big picture is potentially bridging that gap, right? Getting the linear scaling efficiency of state models like RWKV, but adding back some of that interactive power and, crucially, this progressive scalability that transformers sort of lacked and even earlier RWKV struggled with.
And that scalability has real-world implications.
Definitely. Think about continual learning models that need to keep learning over time, or deploying powerful models where you don't have infinite training resources. This progressive scaling could be a game changer.
Makes sense. Cheaper to grow a model than rebuild it. What are they planning next?
They laid out a few paths. One is trying this metastate idea in other state-based models, like state space models, SSMs, which are also gaining traction.
Right, see if the principle generalizes.
Another is integrating metastate with mixture of experts, MoE. MoE is another way to get huge models by only using parts of them for any given input. Combining metastate scaling with MoE scaling could be powerful.
Metastate Mo. Interesting combo.
And finally, just testing it more broadly. Beyond language modeling on the pile, see how it does on various other NLP tasks, translation, summarization, etc. See if the benefits hold up.
Okay, lots to explore. So let's try and boil this down for the learner. What are the key aha moments from this deep dive?
I'd say three things stand out. First, just the sheer cleverness of the self-state encoder, using the model's own state as transformation weights to get that token parameter interaction without softmax. That's neat.
Definitely elegant.
Second, the direct link between that state autoregressive update mechanism and enabling progressive scaling. You grow the state, you grow the model, reusing most parameters. That's practically very important.
Solves a major bottleneck.
And third, the empirical results. Lower loss than transformers, and crucially, that widening performance gap at larger scales. That's the evidence suggesting this is just theoretically nice. It might actually scale better in practice.
Excellent summary. It really feels like this work opens up some exciting possibilities.
It does.
So for you, our listener, here's something to chew on. What happens when models can genuinely scale more organically, more efficiently? Forget just bigger numbers. What new kinds of capabilities might emerge if we can grow AI intelligence more like, well, like something growing, rather than just building bigger and bigger static blocks?
Yeah, it shifts the perspective.
We absolutely encourage you to check out the papers we touched on: Vaswani, Pang, Wang on token former, and definitely Xiao and colleagues on metastate. Think about how these ideas, efficient state, token parameter interaction, progressive scaling, might ripple out into your own fields. Maybe there are connections you haven't thought of yet.
Always worth looking for those cross-disciplinary sparks.
Indeed. Thanks for joining us on this deep dive.